In this lecture, I will go through the different phases of the design process, discuss the role of values, and point out ethical issues in each phase. But let's start with a few examples. This is a technology that will be familiar to all of you, the speed bump. These are intentionally designed to increase safety and decrease speed. They come in all shapes and sizes. They seem quite simple, and in many ways, they are. But they are also part of a larger system involving many different people and stages. They are, quite literally, a concrete form of regulation. Unlike a sign, the speed bump acts on you in a direct, tangible way. It's no surprise that in England, they are also known as sleeping policemen. Or consider voting computers, which are used in many countries around the world. These were used in the Netherlands until they were made forbidden in a 2007 court case. The reason they were forbidden was twofold. First, it turned out that you could find out what somebody was voting by analyzing the radiation that was transmitted during voting. And second, the voting computers did not allow for recounting the votes in an independent way. One just had to trust the computer algorithm. This was against the Dutch law, and thus the technology failed because it did not meet certain ethical and social requirements. Finally, take the common tomato. It might be strange to think of the tomato as a technology, but it is a highly engineered product. Its skin is robust and hardy, so it can withstand the force of farm machines that harvest, sort, and process them. And it is plump and shiny red to catch the eye of hungry shoppers. It has a long life, so it can survive traveling to stores, sitting on shelves, and waiting to be eaten in your pantry without rotting beforehand. And as with any of these technologies, each property, each phase of the system is carefully thought out and designed. So what are these phases, typically, and what kind of ethical issues arise? This figure shows the design process. We start with problem analysis and formulation and setting design requirements. Then on to conceptual design, which is the creation of alternative conceptual solutions for the design problem. After that is simulation of one or more conceptual designs to test how well they meet the design requirements. Then comes choosing one conceptual solution from a set of possible simulated solutions. The design is refined and fleshed out, and a prototype is then developed and tested. This testing may lead to adaptations in the design. And finally, it's time for manufacturing and selling. I will illustrate these design phases, values, and ethical issues with a brief case study of smart meters. These devices record energy consumption in homes, typically in intervals of 15 minutes or less. They allow two-way communication with the energy network. Information on energy use is transferred on a regular or even real-time basis. And the smart meter can be remotely controlled and monitored. It can even be turned off and on from a distance. The smart meter can also provide detailed feedback about energy use to consumers, which can then help them teach how to use less energy and save money. In 2008, two bills were sent to the Dutch Parliament, which proposed to make the smart meter compulsory for every household. However, in 2009, the First Chamber of Parliament rejected the law due to privacy concerns. Smart meters collect detailed data on energy use from consumers and make this available to energy producers. The data, for example, may reveal when people are at home, their living habits, or even what programs they watch on TV. Let's now look at the various design phases for the smart meter. The first phase is problem analysis. This can be subdivided in three more specific phases: problem formulation, values, and design requirements. One can formulate the design problem as design an energy meter that allows for two-way communication between the meter and the central energy system. This seems to have been the way the engineers approached energy meters. However, one might also formulate a somewhat different design problem that stresses feedback to the users and the possibility for energy savings and sustainability. If the technology was motivated by this problem, then we would end up with a different kind of design. Next, we can list the relevant values. In this case, relevant values are reliability, cost, and ease of use. But there are also moral values like privacy, because detailed recordings of energy use may invade personal life. Sustainability, because feedback of energy use may reduce consumption. And security, because the device and its data should be protected. These values then need to be translated into design requirements. Possible requirements in relation to privacy and security are people should be able to choose what data is collected. Sensitive data should not be shared with the energy supplier. Data should be encrypted, and so on. The next step is to create conceptual designs, in which a number of possible solutions are sketched out. In the conceptual design for smart meters in the Netherlands, the device would communicate energy use data at short intervals or in real time to the grid manager, who would share this information with the energy supplier. The supplier would then make the data available on a website, which could be accessed by consumers for the purpose of tracking their energy use. This conceptual design, however, has disadvantages in terms of privacy and security. To provide detailed feedback to consumers, the energy use data needs to be collected in real time or in short intervals. In this design, all data is shared with the energy supplier regardless of its privacy sensitivity. Additionally, the website where users access their data introduces security risk. So what would an alternative conceptual design look like? For example, data about energy use could be shown on a display that can be directly read by the consumer, rather than having to log on to a website. There could also be restrictions on what and when information is shared with the grid manager or energy supplier. This less connected, privacy-sensitive design would, however, miss out on some key advantages of the smart meter, like the possibility to accurately read the meter once a year from a distance to determine the annual energy bill. A third conceptual design could combine features of the previous two. Real-time data on energy use is accessed via display so that the user can monitor their consumption, while also sharing some information with the grid manager and energy supplier for added convenience, efficiency, and accuracy. This data could also be collected on much longer timescales so that it's aggregated, thus increasing personal privacy. However, these privacy features may make the device more expensive, and the limited data collection and analysis may reduce savings. Now let's move on to the next design phase, simulation. In this phase, models are built to predict performance on a range of relevant parameters. Ethical concerns partly determine what type of models should be built and which performance parameters need to be included. European law, for example, now requires a privacy impact assessment of new technology, although it's still very hard to predict how a design will actually score on privacy. The next design phase is choice. Here the concept designs are compared on a number of evaluation criteria. This involves making trade-offs and meeting thresholds based on your desired values. As we saw with the smart meter designs, the first concept does not score well on privacy and security, while the second one solved these issues but did not allow two-way communication with the grid. And the third may address these issues by striking a balance, but perhaps at the sake of affordability. The moral question now is what design to choose? Answering this question will be the topic of another lecture. Once a concept is chosen, the actual design needs to be refined and fleshed out. The designers must address practical details, like, for example, deciding exactly what data is gathered, what kind of encryption will be used, how the system will be maintained, and what is the plan in case of a data security breach. Decisions must also be made about what materials will be used to build the hardware, how will it be installed, will it be sold or rented, and many other key details that have to be addressed. Once a working prototype is made and tested, it's possible that unforeseen ethical issues will arise. Or that issues which seemed very concerning are actually not a big problem. In the case of smart meters, the trial study suggested that energy consumption is, on average, reduced by only 3 to 5%. This raises the question whether this minor gain is worth the loss in privacy. Finally, it's time to manufacture and sell the technology. Just because this is the end of the design phase does not mean that all of the ethical issues and value decisions have been successfully navigated. Some of the most visible problems arise at this stage. For example, where and how will the device be produced? Just ask Apple about its choice to produce iPhones using cheap labor in China who work in terrible, dangerous conditions. This may save the company and consumers money, but the trade-offs are ethically problematic at best. So, in sum, we have seen that technological design involves many phases, and at each phase there are ethical issues, value trade-offs, and choices that will affect every aspect of the end product. The smart meter is just one illustration. Arguably, all technologies emerge out of a process in which many alternatives, which represent different values and choices, are unrealized. The important question, then, is whose interests are represented by the chosen design, and what other possibilities are there? As an engineer and a designer, you play a crucial role in recognizing these values, reflecting on these choices, and responsibly addressing these ethical issues. Thank you.